to implement and show the various algorithm to solve this maze with the minimum state using Python. Class node. I have defined a class called node that in this case is keeping track of the state, the parent, in other words, that state before the state and the action. In this case, we are not keeping track of the path of cost because we can calculate the cost of the path at the end after we found our way from this initial state to the goal. Class stick frontier. In addition to this, I have defined a class called a stock frontier. And if unfamiliar with a class is a way for me to define a way generator the object in Python. It refers to an idea of object-oriented programming where the idea here is that I would like to create an object that is able to store all of my frontier data, and I would like to have a function otherwise known as method on the object that I can use to manipulate the object. And so what going on here? If in Premiere with the syntax is I have a function that initial create a frontier that I am going to represent using a list, and initial my frontier is the represent by the empty list. There's nothing to in my frontier to beginning with. I have an add function that adds something to the frontier. As by uploading it to the end of the list, I have a function that check if the frontier contains a particular state. I have an empty function that check if the frontier is empty. If the frontier is empty, that just means the length of the frontier is 0. And then I have a function for removing something from the frontier. I can remove something from the frontier if the frontier is empty. So check that first, but otherwise, other, if the frontier is empty, recall that I am implementing the frontier as a stroke, a list in first a last in first out data structure, which means the last thing I add to the frontier. In other words, that last thing in the list is the item that I should remove from the frontier. So what we will see here is I am have removed the last item of the list. And if you index into a Python list with -1, that gets you the last item in the list. Since 0 is the first item, -1 kind of the warm up around and gets you to the last item in the list. So we give that the node, we call that node, we update frontier. Go ahead and remove that node that you just removed from the frontier, and then we return the node as a result. So this class here effectively implement the idea of a frontier. It gives me a way to add something to the frontier and a way to remove something from frontier as a stock. I have also for good measure implement and the attentively version of the same thing called a Q frontier, class Q frontier, which in parentheses you will see here it inherits from a stock frontier, meaning it's going to do all the same thing that the stock frontier did, except that we are removing a node from the frontier is going to be sim- different instead of removing from that end of the list to the way we would in the we are instead going to remove from the beginning of the list. Self dot frontier will get me the first node in the frontier, the first one that was added, and that is going to be the one that we return in the case of q. Class maze. Under here I have a different of a class called maze. This is going to handle the process of taking a sequence, a maze like text file, and figuring out how to solve it. So we'll take as info so we'll take as input a text file that looks something like this. For example, here we see hash mark that you are the reporting wells, and I have the create a reporting that's string function, and the character is be reporting the ending the position. The first line initial an empty list called wells that will the store inform about the wells in the structure. The substance nested for a loop iterate thought is row and column of the contents object pres- who is the presumably represent a map or guide. Inside the nested loop and if else statement is used to check the content of each element in the map. If the element is A, it means it represent the string upon string point. So the code assigned the coordinate of the position to the self dot start. Alternatively, int append false represent null to the row list. If the element is B, it denotes the goal position. The code assigns the coordinate of the position to the safe dot goal. Alternative and affirmative false to the list. If element is the blank space, its need cost the empty position to the map, so the code implement false and the row list. For for any other element, it implement the press of oil. Hence, the code appended true to the row list that try to accept the block using the handle any possible index error that might occur if you map decimal extent of range of defined by self dot height and self dot width in case the code append falls to the row and list. After the editing throws all of the elements, the row list represent a row. The map is appending to the wealth list. Let the code here is the point method. The display the map including the wells. It first check if a solution has been found. If a solution extent is against the second element of the self dot solution, trump that solution variable, otherwise is assigned the none. The loop utility throughout each row of the map stored in the wells list using the im- implement function inside the loop. Another loop it's the thought is the column of the current row. However, the code student provide the lacks of the necessary identification, so the should the remutant in the result is the function solve. The more interesting part is the solve function here, where the solving function is going to the figure out how to exactly get from point A to B, and here we see an implement of the exact same idea we saw from the moment ago. We are going to the keep track of how many states we have the explored just so we can report that data later. But I start that I know that represent just a start state, and I start with a frontier that in this case is a stroke frontier, and given that I am tracking my frontier as a stroke. You might imagine that the algorithm I am using here is now depth first search, because the depth first search of DFS using the stroke as it is data structure, and this frontier is just going to continue the start state. We initialize the explored set that until is empty. There is nothing we have explored so far. And now here our loop that nation of preparing something again and again. First we check if the frontier is empty by calling to empty the function that we saw the implement of a moment ago. And if the frontier is indeed empty, we will go ahead and risk an exploring or a Python errors to say, sorry, there is no solution to this problem. Otherwise, we will go ahead and remove a node from the frontier as by calling frontier.remove frontier.remove and update that number of the state we have the explode, because now we have a explode on addition list. So we say save dot save dot number explode plus equal 1, adding 1 to the number of the state we have to explode. Once we remove a node from the frontier, recall that the next step is the c, otherwise not, it's the goal test. And in this case of the maze, the goal is pretty easy. I check to see how about the star of the node the equal the to the goal. Initial when I set up the maze, I set up the I set up this value called the goal, which is the property of maze. So can I just check to see the node of actually the goal, and if it is the goal, then what I want to do is backtrack of my way, figure out that action I took in order to get this goal. And how do I do that? We will recall that every node store its parents, the node that came before its we have used to get to this node, and also the action used in order to get here. So I can create this loop where I am constantly just looking at this parent of every node and keeping track for all the parents what action I took to get from the parents. So this loop is going to keep reporting this process you looking through all of parents and until we get back the until the state. So no parent where node dot parent node dot parent is going to be equal to none. As I do so, I am going to be building up this list of all of this action that I am following, and this list all of the sale that are part of the solution. But I will revise them because while I build it up going from the goal back to the initial state, I am building the sequence of action from the goal to the initial state, but I want to reverse them in the order to get the sequence of the action from the initial state to the goal, and that is the ultimately going to be the solution. So all of that happened if the current state is equal to the goal, and otherwise if it's not the goal, will then I will go ahead and added this state and explore state to say I have explored this state. Now no need to go back to it if I came across in the future. And then this logic here implemented that idea of adding neighbors to frontier. I am saying look at all of my neighbors, and I am implement a function of called neighbors that you can take a look at. And for the each those neighbors, I am going to check is this is already in the frontier. Is the stay already in the explore set? And if it is not either of those, them, I will go ahead and add this new child node, this new node to the frontier. So so there are fair amount of syntax here, but the key here is not the understanding all of the nuance of syntax. Those feel free to take a close look this file on your own to get sense for how it is working. But the key is to see how this is an implementation of the same procedure code, the same idea that we are described amount ago on the screen when we are looking at the step that we made following order solve kind of search problem.